Assalamualaikum warahmatullahi wabarakatuh, and a very good morning or good day. Um, so this is for Mechanism Design Lecture 3. I'm doing this recording instead of a synchronous session. Anyway, we are going to finish up Chapter 1 for the Introduction to Mechanism or Kinematics. And hope you can enjoy this recording at your leisure, and then we will also proceed to start on lecture on chapter 2. So what I'm gonna do is check let me check the teaching plan. You can go through it for a little bit, and before that, let me share my screen. If I can remember how to share my screen. How do I do that? It's over here. So I'm going to share my screen, and that's about it. Uh, all right, so yeah, let's get on to it. So what we have here is the teaching plan, and so we are finishing chapter 1. So chapter 1, we should be finishing it with the topic on Grashof's Criterion. We have talked about the groupless equation or KMOGE, Kurzbach modification of groupless equation, KMOGE, and that is to find degrees of freedom, and that should relate us to the number of actuators or controllers that we need to use for that machine. So if we have a 3 degree of freedom system, meaning we have to have at least 3 controllers, one for each of the actuators or motors or hydraulic cylinders. And then we have to start on the Grashof criterion. Grashof criterion basically tells us if any of the linkage can actually rotate fully, make full rotation 360 degrees. So if it is fulfilling certain criterion, then we can say it is Grashof. Otherwise, not all mechanism needs to be Grashof, because sometimes we can control it using uh, pneumatic or hydraulic arms or actuators. In this case, we do not have to have linkage that rotate 360 degrees or make full rotation. All right. So chapter 2, we will start talking about analyzing linkages or linkage mechanisms, where the plan is to have that being done in 1 week to focus on position analysis, focus on position analysis. And we have a few methods. We have graphical methods, and then we have a bunch of, or at least 2 analytical methods. Okay, hopefully by this time we can assign you a homework. Maybe I'll give it out on Thursday. Homework number 1 will be helping you on doing some of the example questions, so that it should prepare you for the tests and also the exam. Okay, and hopefully we can also start using MATLAB, or maybe I introduce the use of MATLAB in my lecture here. All right. So the next one, let's go to chapter. Yes, chapter. So we are yes. Last time we stopped over here. Maybe if I can backtrack a little bit. Maybe for this example, I guess the drawings did not come out last time, because I was just using the PDF of it, and that PDF did not generate this part. So basically, the top jaw is this part, but if you want to extend to include the back part over here, you'll see I can extend it. So the black part here is actually a continuation of this red part. It is part of the frame, still part of the frame. And here the screw is not drawn that nicely here, but we have the handle of the screw, the knob, like over there, with some knurl, KNURL, knurling, maybe a diamond knurl. And then that is the screw, and actually you can imagine there is a kind of like slider or a nut that is attached to this part, attached to this part number 4, and that is pinned to that nut. So that nut basically do not have to rotate. So instead of that, this one, the screw will rotate. So you have to, is pretty much like how you would use this device. So you rotate this null handle, and the screw will rotate, and the nut over here will slide. So the nut will slide on the surface of the frame. Okay, so that's why when you do the labeling again, you will have the ground to be number 1. This is number 2. This part over here is number 3, and then this small part is all the way to the nut over there is the number 4, and then number 5 is that nut, and then the screw will be number 6. Okay, number 6. So so the screw and the nut will have a J2 relationship, or J2 joint. So that is defined as a J2. So that's why our J2 will be 1 here, and that's between the nut and the screw. And the screw is also being held or being supported by the ground or part of the frame, and that relationship between the screw and that frame is F here. So that's a J1, and the screw is point number 6. Okay, so You label them like this, and then plug in the numbers. So you see we have 6, and our n is 6, and let's see our J1, A, B, C, D, E, and F. So if you calculate A through F, it will be 6, A, B, C, D, E, F. So that's 6, and we have one J2, one J2. Okay, so we got all those numbers, and if you plug it into the KMOGE equation here, 3 times 6 minus 1, so 6 minus 1 is 5, so this term will be 15, minus 2, our J1 is 6, so that will be 12, and this is 1, 12, 1, so this is a total of minus 13. So 15 minus 13, our F will be 2 degrees of freedom. So if you look back in this complete system, 1 degree of freedom goes with this handle. That's how you use this device by applying force over at this lower handle or lower grip. And another way is to control by using the screw over here, screw knob. Okay, so if you turn this a certain way, and this one will give a different input. Okay, so that's why this and this will be independent. Independent. So they operate independently. All right. So that's is the case. Okay, let's move on to the next one. Let's take a look at our 4-bar mechanism. So basically, from the things that we have learned, we have learned Grubler's equation, and now we take a look at the 4-bar mechanism. And like I said, 4-bar mechanism is the focus of our study. Because there are a lot of other mechanisms. Like I said, we can have 2-bar, but that will be too easy. And we can have 6-bar. That's another single degree of freedom system. But 6-bar, actually, if you take a look at it, you can see it's the the small unit inside the 6-bar is a 4-bar mechanism. So basically, you have two 4-bar mechanism inside a 6-bar. All right, so usually the ground we will always label it as number 1. 2 is the driver or input or crank, and then this coupler is link number 3, and follower is the output, and that is link number 4. And in this part of the analysis, size does matter. So we will look into what are the lengths being involved here. So we need to find what is L1, L2, L3, and L4. We need to know that because different lengths will determine how this device or how this mechanism work or behave. Okay, so we take a look at this equation or inequality, or we just call it Grashof's criterion. So it says that S plus L, shortest plus the longest, must be equal or less than P plus Q, where P and Q are the other two lengths that are not the shortest, not the longest. Okay. Okay, these are some, but I'm not sure whether they are correct or not. Sometimes there are some corrections being needed. So the first one on the left here is we call it drag link, where S plus L is less than P plus Q. Okay, we got this kind of machine. Uh, full revolution for both links. Okay, so when I said if something is Grashof's, at least one link is able to rotate continuously. But in this case, both there are two links that can rotate continuously or full rotation. Okay, so that's good. And then we have this situation, also a Grashof system, but here we have there are certain further condition on which part is the ground. So in this case, maybe the shortest is the ground. So you'll create this kind of mechanism where it's called drag link. With two links, the input and output will be the one that can rotate continuously. Whereas over here, the shortest link is the crank. So this one will be able to rotate continuously. Okay, so there is a different here. So here the shortest link is the frame or the ground. Here the point Q is the ground instead. All right, here the next one we have a double rocker. Double rocker. So in this case, double rocker. So the input and output will just rock. Rock means it just rotate back and forth, just like a rocker playing the guitar in a rock concert. So, but here just moving L and P just rock back and forth within this line, shown by the trace in green. And the last one is a parallelogram where S and P are same length and Q and L same length. So a lot of parallel situation here. So in this case, we have at least two links, just like before. Two links here will be rotating in the same manner. So it's just like a copy. So this one moves certain much, certain angle. This one will move the same angle. So there are a lot of engineering application, consumer product application that use this one as well. Okay, so this one is for another situation. And if I'm not mistaken, there is another situation where it is there's another situation not shown here, but maybe another situation, another slide I will show you that where this part is not L or P, but rather this part will be able to rotate continuously. So that is the part that is not, sometimes people miss that. So in that situation, this equation will be S plus L less than P plus Q. Okay, but that situation will show that S will be the one that rotate continuously. Okay, so the same mechanism or same setup, but if you change the part that is fixed, the part that becomes the ground, So you will have a different mechanism as a result. So if I change from this part as the ground to this part as the ground, so here we have a double crank, double rocker, double rocker. Okay, this is other than four bar mechanism. So slider crank is the other common mechanism that we should be focusing on, and slider crank is also a single degree of freedom system. So like this one, if I move the crank, this slider will move or slide to the left or to the right accordingly. You cannot move independently. So if I move the slider, the crank will have to follow accordingly. So you cannot say I want to stay here or I want to move the other direction. No, it cannot. So because this is a 1 degree of freedom system, you either control the crank and this one follows, or you control the slider and the crank has to follow. Okay, this one is called the inline slider, where the center of the slider, if you trace the line of action, will pass through the center of rotation for the crank, okay, or the pivot of the for the crank. Whereas this other one is called the offset slider crank. So this one, the line of action for the slider, if you extend it, will be will not pass through the pivot for the crank. Okay, so here is the pivot. Pivot ni paksi lah, paksi putaran. So this one will not pass through that paksi or pivot. Pivot is a pivot. Pivot. If I can write it over here, so pivot. Pivot is a center of rotation. So here we have many pivot. How to change the color? Okay, so we have this is the fixed pivot. And this is a moving pivot. So this is moving pivot. This is another moving pivot. Okay. And that's about it in this section on this chapter. So if you guys want more reading, you can go look for this book, and perhaps it can help you understand this a bit much better. Okay, let me stop the. All right, so the other one will be this one. This is in the next chapter. The next chapter. So if you have any question, you can definitely ask me or message me. Send me a message, and I will try to get back to you as soon as possible. Okay, but for now, let me go ahead and run this one. Okay, for the position analysis. Position analysis. Why is that? Hmm. Pointer option. If I want to choose the laser. Okay, so that's the spotlight. So this not PowerPoint, so something else. So anyway, okay. Hmm. How do I control this? Okay. Sorry about this. Let me stop this sharing for a bit, and let's see if I can. Uh, if I can. I can reopen this file using PowerPoint instead. Okay, let me try to share that my screen again. Okay, reshare it. Sorry about that. Uh, all right, so now just run this thing. Okay, and then maybe use the laser. All right, so position. So if we have a link, so this whole thing is considered as one link. Same body is a ternary link. So we have one point, and we can have one another point here and a third one over there. And let's call this point over here is label as A. And if we turn this body certain angle to clockwise, so A will be over here, A prime. And since this is a rigid body, so everything we can pretty much know, or we can analyze so that we know also the position of this point. This point, provided this angle is preserved. This angle is preserved, so we can predict what is the position of this point over here, this unlabeled point over there. So there are many ways to do that. One of it is to use vector. We can use vector as one of the tools that can help us understand this problem or solve this problem. So scalar usually will have value or numbers, but probably we don't attach, or we don't we might not know the direction of it. So we have the value, the magnitude, but not the direction. So like volume and also time. So I guess time is always going to increase. Um, then whereas vector, we you must have the value and also the direction. So for example, forces, if you want things to go up, so that force must be pointing upward. Whereas if you have gravity, for example, so meaning that force will be pointing downward towards the center of the earth. And displacement is also important, or that means position can also be a vector. So it matters whether you are pointing to the right or to the left, up and down, or any other directions. So here position is a vector, and velocity comes from the position, because the definition of velocity is basically the ratio of the difference, the change in time. Sorry, change of position with respect to the change of time. Okay, so that's basically velocity. All right, some review of vector, how to understand vector, so that we can use it. So vector is basically or usually depicted as an arrow. So arrow, we have the tail and you have the tip or arrowhead. So usually the length of the arrow will determine the magnitude. So you want to draw, or you want to correlate between the magnitude and also the length. Okay, if the magnitude is bigger, meaning your arrow should be vector arrow should be longer. So that can be used as comparison between other vectors, among other vectors. And then the sense is referring to the direction, and usually the direction is given by angle. So it is important for us to always measure or locate or measure the angle in certain ways. So I like to encourage you to always measure or, or notify your angle from the tail, instead of sometimes from the tip, sometimes from the tail. So always do it from the tail. And we want to define this convention. We have to follow certain convention. So angle 0 is always pointing to the east. Look east, or in the positive x direction. So 0 is over here, 0 is over there, and positive going counterclockwise, meaning after 0, the 90 will be over here in the north. North is 90, west will be 180 degrees, and south will be 270 degrees. Okay, so that's how we want to define things. I think if you use AutoCAD, usually the setting is already like that. So you look east is 0 degrees, north is 90 degrees, west 180 degrees, and south is 270 degrees. All right, and then a lot of these problems, we can see a lot of triangles in them. So, just bear with me before we get to see an example. But take it from me, we are going to see a lot of triangles. So we need to revisit this triangle, and it can be related to cosine law and also sine law. So I guess between sine and cosine, I guess cosine law is more prevalent. So you want to use this a lot more, the cosine law. All right. Uh, in our case, a lot of stuff is can be considered as 2D problems. So meaning even the forces or the position or the velocity vectors can be depicted in a 2D situation or 2D as a 2D problem. Okay, so and as expected, you can have this vector, and then you can break it up into the components, components along x and y direction. Okay, so here if this is vector r, so the rx is this part, whereas the vertical part is ry. And basically, this is the notation that we want to use for the vector. So if r is the vector, you want to put the uh, arrow cap on top of it. So another way to do it is by using making it bold. R is bold, but I think I like to use this one instead. And you can represent this vector as this one, the components. The components. So if you know Rx and Ry, so basically this is what it defines. Or if you don't know that, so basically you know the magnitude and also the direction. So probably you can also find this information. So here we put cosine as the x component and sine for the y component. So we can take a look at this other example is using forces, a bunch of forces for this example. And we are told we also have vectors or the other two forces at E and also at F, which are not fully defined yet. This one is fully defined. You know the magnitude and also the direction. Magnitude is 30 Newton, whereas direction is 70. This one, the magnitude is 20 Newton, and the direction is 20 from here, but from the x, positive x, that will be, direction will be 160, 160. Same over here, so this is 15 degrees from south, but this is the magnitude, but the direction here should be labeled as negative 70, negative 85. No, negative 75, negative 75. And this is another known vector, 7 Newton, and the direction is 30 from this direction, but from the positive x, that will be 150 degrees, 150 degrees positive. So we are left with these two other vectors. So this one, meaning the direction is 45 plus 90, so 135. So this one is the direction is 180 plus 20, so 200, 200 degrees positive. All right, so what I'll do is we set an origin and then just get all these known vectors over there, we put one after another. So for example, this is RA, this is RB. At the tip of RB, you have the tail of RC. So this is RC. And then we have RD. And we are left with the other two, RE and RF. So we just try to copy this thing and bring it to that other part. Okay, and then we want to get the intersection. So once you get that intersection, everything's done. Everything is done. Okay, so this in this box is called the vector equation. So in this case, we have RA from the origin, RA, then plus RB, plus RC. So all these things pointing in all different directions. And then you have RD. So once you have RD, you can also plus that with RE and also RF. But then you know that RE and RF are not solved yet. They are not fully defined yet. So you can bring it to the other side of the equation. Okay, basically the red one and also the purple are the same mechanism, four-bar mechanism. So the initial part is in the purple color, and then the red is the new position. So if you are given the position of B1 and also B2, or by maybe giving you the angle here, we can find what is the new position for C2. So here is the continuation of that. It's being broken into several steps. So we have the origin at A. So you can define this to be your 0, 0. Then label all the pivots, moving pivot, and also fixed pivot. So A, B, C, and D. So A and D are fixed pivots, whereas B and C are moving pivots. So here R2 is at 45 degrees like that, or if you measure from positive X, this angle will be 135. Yep, so this one is shown. Theta 2 will be 135 CCW. So if you solve this through graphical methods, so you have to solve it very accurately. So you can decide whether you want to use graphical method, but using AutoCAD, or you want to use manual drafting. So here, basically, if you already know the second position or new position of B2, and since you know R3 will be maintained, as well as R4. So you can scribe an arc like that from B2, and from here, from D, you can scribe R4, and then you get intersection. So meaning this is the location for C2. That's the location for C2. Okay, and then just complete the mechanism and just move on from there. Okay, and then for mechanism, 4-bar mechanism, actually we have two possible situation, and this circuit one, so circuit one will look something like that, and the other one circuit two. Uh, you see the coupler will be crossing like that. So this is one is on the top part, whereas the other one is on the bottom part. Okay. All right. For analytical method, so graphical method is done. For analytical method, there are two ways. So one way is to use this equation. If you look from the book by Mishka, so basically he has done all these things, and the same set is this is for circuit number 2. So I guess the top two is the same, but when you get to theta 3 and theta 4, it's a bit different. And then lastly, we also have equations, closed form equations for slider cranks. And yep, so you need to know what are the lengths, R2, R3, and also R1. Well, I guess it's a good place to stop, and we'll continue this on Thursday. So let me stop my. So if you need some, if you have any question from what I have just presented, or any part of the lecture that you do not understand, please let me know. Again, thank you very much, and I will see you on synchronous session on Thursday. Assalamualaikum. Have a good one.